into shared memory for each atom are the x, y, and z coordinates, the charge for the atom, and what they call a size parameter, which has to do with this Son-Boltzmann equation. And so that's sort of like a radii for each atom. And so the bad part about this is it ends up being 5 things and not exactly 4. 4 is a magic number for the GPU because we have these floating point types. We have float, float 2, float 4, and those happen to be the ideal memory transaction sizes for each thread on the NVIDIA GPUs, at least. If we had 4 items, we might, instead of floating them into separate register variables, we might load them into a single register variable. So that might make the code easier to read and write, and it might improve our global memory bandwidth. So because we have 5, it ends up being a wash, and so we can simply load, we just do a little test, and until we run out of atoms, we basically loop over a group of atoms, loading them into this shared memory. One thing that's interesting to note here, in the global memory indexing, we're just increasing by one of these. This J atom is based on our thread. So let's see if I have that right here. Yeah, our thread in I atom and J atom, one is the loop and the other is the thread. And LID is based on the thread. And so this is this is based on our thread dimension in X. And so, yes?
Question on the size and the charge.
Yeah.
In most systems, they're going to be similar for lots of the same atoms.
Yes.
Is there no way to, I don't know, store this constant and then pick it
Well,
as
these could be constants. We could store them in the constant memory. So this is another interesting thing. This kernel was written after we had some of the newer GPUs, like Fermi, that has hardware cache. And so in this kernel, we don't do anything with constant memory. We're just accessing global memory in a friendly way. And so we don't have to do anything special there to make use of that. It might be interesting, if you knew something about that. Let's say we only have here two different quantities for each atom other than the coordinates. What if we had 15? Or what if we had a bunch of other atom type information? If we had more than just charge and size, it might pay off to have a lookup table in memory, and instead of storing all that data in a raw form with each atom, we might instead have a unique lookup table for each atom species and go fetch the similar items out of that lookup table, and that would potentially decrease the in-memory size of the per atom data. But that then costs us having to do 2 memory accesses to get those things. So if we need to access those quantities really fast, and in this case we do, it may be a better idea just to do it the hard way like this. And so this is one of those trade-offs. How much memory do you use in that constrained on-chip shared memory versus how many memory lookups do I have to do to actually retrieve the value that I care about? So that's an interesting design trade-off. I think when Dave talks about the molecular dynamics kernel, this comes up again because besides these sorts of atom parameters, you have various rules for combining the different atom type interactions and exceptions to these, and you have to deal with that stuff in the molecular dynamics kernel. And so there's a little trickery involved in making that efficient. And Jim can probably comment on that too. So what I was going to say here, though, is in the global memory lookup, we're just indexing on a simple function of the thread index. In shared memory, have you guys learned about bank conflicts? Mm-hmm. Okay, so you learned about bank conflicts, so that's good. So that's the reason why in the shared memory store, we're computing the shared memory index, basically taking that local ID and adding it to this L size, a multiple of L size. And that L size is there so that the shared memory writes are occurring in such a way that there are no bank conflicts. So they're in sort of separate lanes of shared memory. So by doing that, both the global memory read ends up being coalesced and the shared memory write ends up being conflict-free. And so that's running at a relatively high performance. And we have to have a sync threads before here and a sync threads after before we use. So this is important. It's very easy to make this mistake of thinking, oh, the first time through you don't need the sync threads, but after, you'd either have to have a sync threads before you do this or a sync threads after the reference to it, because you're going through a loop, so you have to imagine it in its unrolled form. What is the sequence of sync threads operations? People often forget to put the sync threads both before and after to space these out. And so using the shared memory is very simple. We just basically loop over all the atoms in shared memory and accumulate this potential. And you can see that the equation for that potential is far more complicated than just the the charge times reciprocal square root of the distance. In this case, we have a lot more arithmetic involved. And what that means is, with a kernel like this, we don't have to try anywhere near as hard to eliminate memory references and things like this. The arithmetic is costly enough on a kernel like this that we actually do a pretty good job with the very simple kernel like this. So this is something to think about. As you start looking at your own problems, the choices you make, where do you put your effort in terms of optimizing the code, it depends on how complex your arithmetic is. The more complicated your arithmetic, the easier your job will be, so long as you have enough parallelism to keep the GPU busy. If you have very little arithmetic, and it's mostly memory bandwidth bound, then you're going to spend a lot more time coming up with ways of either getting the working set of the data that you're trying to operate on into the fast on-chip memory, or using things like reduced range or reduced precision data types. So to store that memory in the on-chip, or store that data in the on-chip memory. So, for example, one person mentioned they were interested in doing single particle reconstruction, things like this. Question you would ask yourself with such a code is, do I need to store my density values in a full 32-bit floating point number, or is there really only 8 bits or 16 bits of precision or less? And if that's so, maybe I can use an integer, that's been scaled, so I can use a fixed point representation of some kind, or something else to squeeze more of those values in the on-chip memory, make better use of the GPU's shared memory and caches and things like that. In this particular case, we need the floating point numbers, but there are a lot of cases out there where you don't need even a 32-bit floating point number. You can do a lot with less. So I'll give an example of that in computer graphics. In computer graphics, we often calculate surface normals that are associated with the vertices of triangles. In many cases, for the purposes of shading images on the screen, we don't really need a surface normal that has full 32-bit precision on each of those direction components. It's perfectly adequate to use what they call a half floating point type, which only has 16 bits total, which is something around 12 bits of mantissa and a few bits of exponent. So very small floating point numbers. So by doing things like that, we can make even better use of that on-chip memory. And so that's something to think about. Can you use a reduced range? Can you use fixed point arithmetic to squeeze more of your data in that small on-chip memory? So that's something to think about. So you've seen the direct Coulomb summation algorithm before. I'll just go over it real quick. So basically, in a manner similar to the multiple Debye Huckel kernel, you're summing contributions to a bunch of lattice points that are sort of in a 3D grid, so sort of like a Rubik's Cube. The potential equation can be simplified down to the point that it consists of very little more, at least inside the kernel, of adding the scaled charge by the distance there. And so the thing that we're dealing with in this algorithm, we have a tremendous amount of parallelism, far more than in the last algorithm. So in this case, we have a lot more parallelism to work with, but we have a lot less arithmetic for each grid point. So the challenges are a little bit different. With the last algorithm, a very simple kernel did the job. We didn't really have to do too much to optimize it, just some simple arithmetic factoring. For this code, for our intended purpose, single precision is adequate for the job we have in mind of placing ions or computing one of these electrostatic maps for visualization. But we can improve the accuracy of these calculations further either by using double precision arithmetic in the summation of those potentials, or by using what's called compensated summation. Are you guys familiar with compensated summation? So compensated summation is basically a scheme where you use two floating point words or registers to more accurately represent a number using that fixed size. So if you have hardware that only has single precision floating point arithmetic, you can approximate, it's not quite as accurate as a full double precision number, but basically you're aligning two floating point words by setting their exponents in such a way that they are, their mantisses would be contiguous, and when you do a floating point operation, you take what would have been round off error that would have been destructively lost, and you apply it to the other floating point word, and in this way, when you're accumulating things, for example, potentials which have a wide range from very small numbers to very big numbers, rather than having floating point cancellation destroy your accuracy, you keep those bits that would have been lost in the other floating point number. And at the very end, after you've summed all the numbers, you can take those two accumulators and combine them back again and get those numbers back. Get the floating point values that would have been truncated. You can add them back in. And so this is good for an algorithm like this because we might be summing billions of numbers, some of which have very large magnitudes, but the majority of which have tiny magnitudes. And so if you throw away, all it would take is for one value to get into that accumulator that's a large magnitude, and it will decrease the accuracy of all the small numbers that are summed after that. And so by using either double precision accumulators or compensated summation, we're preventing those values from being truncated and from being lost. And that can end up being a significant fraction of your total potential in a calculation of a large area if you're doing a very big volume in a sort of all atom contributions case like this that's quadratic complexity.
How expensive is compensated summation?
So it's about, for what would have been one floating point operation like a floating point add, it becomes something like 6, if I remember right, approximately, give or take. So it becomes about 6 operations, and basically because you're doing it to two floating point words, and in order to figure out the truncated part, you store the number, you basically copy the current state of one of the accumulators to a temporary register, then you add the value that you intended to add, then you subtract those two and get what was actually kept, and then you figure out how much you lost from basically the rounded, the truncation error, and then you put the truncated part onto the other accumulator. And so in fact, you can keep going with this. It doesn't just have to be 2. You can actually chain a whole bunch of these accumulators together. So for example, in ocean modeling, climatology, when they compute wave heights integrated over thousands of miles in the ocean, they get very, very small error like this gets accumulated billions and billions and billions of times. And so they often use 128-bit floating point arithmetic or even larger, or they use techniques like compensated summation so that they get accurate predictions of wave propagation and things like this over thousands of miles of open